Well, thanks all. It's a pleasure to me to introduce Yannis Semertzidis. He is one of the names in the field of axion dark matter detection. Among all the milestones in his successful career, I think that one of the more impressive points that he was the founding director of the Kai Center in Korea, one of the most outstanding places in the world for axion dark matter in particular, and an example for those that are trying to start up with different projects all around the world. So it's very impressive. So today, Yannis, with his innovative mind, will present something very new. I know a little bit about it, and I have to say that I'm eager to know more. So thank you very much, Yannis, for being here.
I want to thank you for the hospitality you've shown me here. It's an amazing place. It feels like home. I'm originally from Greece, and the people are extremely nice, very kind. The place is amazing. You are very lucky. You're also very lucky. We are all very lucky because we do science. I mean, 100 years ago, only rich people could afford this. And these days, we can do it, right? It truly is. I hear myself here. It truly is an amazing phase in what we do. The talk is about coherent readout and the search for axion dark matter at the quantum limit. The point is, when you look, you try to observe a signal and you know the frequency, is it something you can do about it better than we do right now? In axion, I can tell you, our noise is dominated by the readout electronics. It's a shame, right? The signal to noise is very good. It comes out of the system, but then we ruin the signal in order to read it out. So think about it. And that's prompted me into going into this direction. If you know the frequency, maybe you can do something about it. So, dark matter, of course, is important. You know this, right? And also, axions are a leading candidate because they come from the solution of the strong CP problem. And I have to say, even though this is not entirely true, the technology is here. I mean, 20 years ago, it was impossible to go beyond a gigahertz. Even 10 years ago, it was impossible to think about beyond 10 gigahertz, right? Now, DALI is providing us a realistic opportunity to get into the high frequency up to 100 gigahertz. And now is the time to think about integration, how we can put all this together so we have the critical mass, the critical infrastructure so that we can make it happen. So what I will present to you is a paradigm, a new readout paradigm that is based on phase-sensitive detection. All right. I'm not trying to get the energy out of the signal because it doesn't have enough. Maybe we can get the information out of the signal. So I asked ChatGPT to make a picture of that. This is the only time I use ChatGPT over here. It got the axion dark matter, and this is the new project we are working on, a coherent spin polarimeter at the quantum spin level. It just came out. It's very interesting. You may want to take a look. The MRI picture looks okay. I don't know whether this is what you use for the readout of CMB. I just don't know. I have to, since the others are correct, maybe this resembles a little bit reality. Anyway, this system can be used, what I'm going to present today can be used for all of those cases to just streamline the readout. So the readout, every time we open up a frequency, a new frequency range, we get panicked. I mean, who's going to do it? There is a whole army of people that need it and babysit the program, and then you do it on the bench in the lab. You put it down in the experiment, and it doesn't always. The ground is not always perfect, and so on. All right. So the traditional way we do these things is we have a resonator, amplifier, power detector. All right. So the signal must provide enough energy, otherwise it's ruined. And we've done that. I mean, this is from our big experiment in Korea, which is still going, by the way. We knew nothing, and we got to be the best in 5 years. 5 years is what it takes to be from zero to the best in the field, if it's really important. Then radio astronomy, what you do, axions, I can tell you, our readout electronics is ruining our chances with quantum noise level. NMR, I can tell you that is also the case. If this succeeds, we can have better NMR, maybe even cheaper NMR, because we can afford to work at lower fields. All right, and then microwave sensing for other things. So the idea is, what if information and energy were separated? All right. So the weak signal carries information, and the reference field carries energy. Now, suddenly you don't have an energy problem, right? You just worry about the information. And then you mix them coherently, and you have a chance. That's the idea. All right. And the question is, can a weak signal modulate a strong carrier before the dominant readout noise is introduced? That is the question. Okay, and I'll try to convince you today that this is worth investigating. We just had the publication out, and we want to try this. So caramel, we call it caramel. It wasn't my name, it was my colleague's. He came up with it, and you'll see how he came up with that. The electric field of the signal. So we go after the electric field, and then we inject reasonable power RF into the microwave cavity. That's called probing. And then you have a power, detected power, and suddenly you get this cross term. That cross term has the information, and if you look at it, it suddenly even has enough energy to go over your readout noise. So that's the idea, right? And then the mixing needs to be done before you mix any electronics. The key thing is you have to have a nonlinear system detect this before you introduce the noisy electronics. All right, so you need the photodiode. You will get the photodiode out, and then you will do it. So if we can use an electro-optic crystal to sense that, so that you sense the electric field, then you use the photodiode. The photodiode will mix them, will mix the signals, and suddenly you will get this. And it's beautiful because suddenly everything can work. All right? And that's where the name came from. Cosmic axions revealed via amplified modulation of the ellipticity of a laser. It's a mouthful, but it's a caramel. Maybe you'll remember it. Okay. Okay. You have a microwave cavity, a TM010 cavity mode, and you're supposed to get inside the cavity, the electric field due to quantum field fluctuations, I mean, you don't have a real photon, but you have quantum field fluctuations so that it looks like it's equivalent to one photon. It's equivalent to 1/2 photon, but let's call it 1 photon for a moment, all right? And that is not enough to produce any reasonable ellipticity on a polarized laser light, all right? So the idea is to inject some RF at the same frequency here. So you do have a reference signal with a lot of electric field. And then the axion coming in, and because of its coherence time, it will have for a gigahertz axion, the quality factor is 10 to the 6, so you're getting a kilohertz sideband. So that's the whole idea, all right? How we do it? We have a microwave cavity that's down below in 20 millikelvin. We had our system at 20 millikelvin, by the way, big 37-liter cavity, all right? And we could put probing a signal into that cavity of the level below a microwatt. It's not a problem at all. And then you weakly couple it to an electro-optic crystal where we run a Fabry-Perot resonator. It's a typical ellipticity system. And then you read it out with photodiodes at room temperature. So that would work very well. So that is the idea. And for those who know about free spectral range and so on, it's not a problem. You can choose the distance between the Fabry-Perot resonators such that you get 10 gigahertz, 20 gigahertz, and so on. You can do that. And you have to move very little. So that system can have a readout from 10 gigahertz to 50 gigahertz, actually from 1 gigahertz all the way to that, with quantum noise sensitivity. That's the target. Are we going to succeed? We don't know. We don't know, but this is what we want to do. For those who don't know, we are using the Pockels effect, lithium niobium oxide 3. All right, this is typical electro-optic coefficient, and you have the phase retardation is that much. When it's 45 degrees is half of that, the phase difference. Now, if you try to do that, just go with electro-optic crystal, you're going to fail. And it's the reason we haven't done it yet, all right? There is one crucial step missing, and that's called the heterodyne variance method. I also like to call it probing, and the way this thing works is you put in power into the cavity, and then you use a bolometer or an electro-optic detector with photodiodes, all right? And look at this. What you're going to get is the signal, the reference signal is going to be phase modulated. So it's going to be modulated, and that modulation over here is what you're looking for. This is the local oscillator, and then you'll see the kilohertz. This is for 1 gigahertz case, all right? Instead of the power detector, we propose to use the electro-optic effect and a Fabry-Perot resonator. And suddenly, the whole thing would work. Why do you want to use that? We have a lot of experience with electro-optic crystals, and the electro-optic crystals has an immense bandwidth. We first suggested and showed that you can get sub-picosecond resolution, or when an electron or bunch beam can go near the electro-optic crystal, it will create ellipticity, and it's very fast. they are using this at the LCLS, at SLAC, to characterize the longitudinal profile of the electron, very short pulses, electron beams, all right? Because if you do it wrong, the beam will look like a banana, all right? Whereas they want it to be straight. So that's the reason. And we know we can use this system for extremely fast and very large bandwidth. It's almost magic. Look at this now. It's too many equations. I don't have a chance to go through it, but I can tell you what is the conclusion. What you see over here is the dark counts of the power detector. So you can say the power detector is very noisy. How do you have a chance to detect a single photon? You don't. All right? If you do, let's say you do, this would be for a 1 gigahertz system. The single photon, by the way, is a kilohertz. This is for the axion case. And if you are in this range, adding any probing would move you in this direction. So you would make matters worse. But if your detector, single photon detector, is sitting here, which is most of our bolometers in this case, and photodiodes and so on, what you do is you inject probing photons and you move in this direction. And suddenly you get down to the quantum noise level. This is the quantum noise level. So it's magic, all right? But go through the equations and you'll see that we recover quantum noise level when we do this, all right? That's the whole idea. If you go out and you get nothing else from my talk, it was worth it. I mean, this is the whole idea of my talk, right? Can always reach QNL, quantum noise limit, even when the power detectors are noisy, by injecting more probing, I should say, enough probing photons to get you into this region. That's the whole idea. Okay? So what has been done and why it hasn't been done so far? Nobody thought of the probing. That's the reason, all right? In 2011, there was a very nice paper published. And what they got is they had a RF power, right, at 1465 gigahertz. The instantaneous bandwidth is about 60 megahertz. And the limit for signal to noise ratio of 1 is 3 picowatts, all right? That's what they've done. It's a beautiful system they've done. What we want to do now, we want to go from picowatt level to 10 to the minus 19. That's the quantum level. That's pico is what? 12. We need 7 orders of magnitude in power. In the electric field, we need 3.5 orders of magnitude. So you'll see how we plan to do that. They are not using probing, all right? This is how they've done it. The resolution bandwidth they use 3 kilohertz. In our case, it would be the axion, which is for 15 kilohertz, all right? And it's a beautiful system they used, absolutely beautiful. And so on. They try to get enhancements and so on. And so they are getting of the order of 440 photons within 3 kilohertz. Right. So let's see what we can do. In our case, we have 3.7 liters. The quality factor of the cavity is 10 to the 6. The axion bandwidth, 15 kilohertz. And then we have 24 microvolts per meter. So we get with a laser of 1 milliwatt and a Fabry-Perot resonator finesse 300, then we'll get this much. This is the shot noise, 10 to the minus 8 radians per hertz. I've done my thesis on ellipsometers, so looking for axions. So this is typical. All right. One axion bandwidth, 68 microseconds. It gives you this much radians, all right? A microradian within the axion. So this is not easy to detect. And then the electro-optic, you see the shift is small, 60 picoradians. That's the typical case, by the way. But with probing 100 nanowatts or 0.1 microwatts, you're there. You get a huge enhancement. And the whole thing is you have a noisy detector, you inject probing, and suddenly you have the sensitivity to do it. What's the sensitivity? An SNR of 17 is not bad. I mean, this is what you want to target, to have something robust, and that is wide, with wide range. All right. So this is the idea. To get an estimated SNR of 10 to 20. And this is what we want to develop. That's it. That is our project. It's not done, and we want to develop that. This is, we want to put a proposal to develop that. If it succeeds, it will have a wide range of implications in many things. At any rate, it turns out if we run that, then we can have from 0.5 gigahertz, all right? This is 10 to the 6 quality factor. It's the best you can get for the axion systems, axion cavities. Above that, it doesn't pay. And we would have below 1K, we would be able to run. Blue is 50 gigahertz, and this is 10 millikelvin, 0.5 gigahertz, and we would be quantum noise limited. All right. Now, the high frequency one is scheme by Dali, is the new opportunity that we want to take advantage. All right. You have any questions so far? It's surprisingly simple. And this is the thing about this, it's say, why it hasn't been done before, right? But I'm in this business a long time, and if you need one breakthrough thing, it's done. People are smart. If you need two things, it's not done, all right? It's hard to think in 2 dimensions. It's just hard. And 3 dimensions, it just takes, and this thing requires many dimensions, so it's not just one. Okay, that's the reason, and hopefully we'll get it moving. The dark matter, on the other hand, it's one of the most important questions in our physics today. And it took Vera Rubin to really establish this as a problem. It was done, said before, and so on, but it didn't sink in. With Vera, it did. She took measurements meticulously, and it was obviously, this is more than 5 sigma difference. There's no question about it. All right. And then they checked it, back then in the 50s, 60s. She was a woman, so people didn't believe her. And then they went after it. They found that she's cool. All right. And not only one, all of them are like that. Almost all of them. And because I'm here, I want to emphasize this. It's important to find a galaxy that doesn't follow this, all right? That is, find a galaxy without dark matter. It's possible because of colliding galaxies can lose their dark matter. And if you can find that, then you prove that Newton is correct. I mean, it's extremely important. I cannot emphasize enough. This is an important contribution you can make. You can find a galaxy without dark matter. I know there have been announcements, but still, all right? It's an important question. On the other hand, QCD, an amazing theory, has a big problem. It's not a small problem. It's a 10 order of magnitude problem, all right? So to solve that, because why was this important to solve? Because without solving this problem, Frank Wilczek and others don't get the Nobel Prize, okay? Because the beautiful theory that solves and fits all the data, it's absolutely amazing, but it has a big problem in terms of CP violation. And the EDM of the neutron tells us, you know, you have a problem. But the axion solves it. And because it solved this problem, Frank Wilczek called it axions. It was a cleaning agent in his kitchen cabinet, and because of the axial current and so on. That's why he called it like that. I like better the Hickslet name by Weinberg, but Weinberg conceded and said, okay, let's call it axion. All right. Maybe if we discover it, we can call it Hickslet back. We can put it. Dark matter is a big part of our universe. It's not small. It's 27%. All right. And in general, we put together review articles, one by John Ellis and the other with Sangbu and myself. That's the experimental part, and this is the theoretical part. And also, what can solve the strong CP problem? An amazing paper by these people. Look it up. I mean, you cannot get around the strong CP problem. It's a beautiful analysis of that problem. It's not just a trivial parameter. You set it by hand and you're done. It doesn't work like that. All right. The couplings of axions, you have this electromagnetic. This is what we use for microwave cavities. This is oscillating EDMs with a gluon field. You need to show that before you call it hadronic axion, by the way. And then you have this as well, pseudo-magnetic fields. The thing about axions is they are coherent, all right, depending on the mass. So you can have one experiment here, and when we discover it, we'll have that, and then we'll have one over there and measure the phase and see they will be moving together. It's an amazing concept if you think. So it's a cosmic maser that is absolutely amazing if you think about it. But it holds the galaxy together. And the situation is a little, okay, this is post-inflation, and you get axion coupling versus the axion mass. You see over here, it's a log-log plot. That's the problem. For post-inflation, you get a range from here to there, all right? And most of it is empty still. The axions in the yellow band solve the strong CP problem. Anywhere else, they are called ALPS. And there is a bottom line. You cannot play the game with a wing like the WIMPs. It's a bottomless pit, essentially. You have to do the experiments, but you don't know, have you excluded the WIMPs or not? So how do you do it? Pierre Sikivi in '83, he said you can use a microwave cavity, enhance it by the quality factor and so on. And now you can have 20 or something like that yoctowatts. I mean, yoctowatts is 10 to the minus 24 watts. Your cell phone to work, you need microwatts in order to be able to recognize who you're talking to. I mean, this is the reason. So why do you think we can do it? Because we are at cryogenic temperatures and we use special equipment and so on, quantum level equipment. Within industrial level systems like huge magnetic fields, strengths, and so on. All right. We started this business in 87. All right, next year will be 40 years working on this. So I was with Rochester, and back then it was not the mainstream, you can imagine, to look into axions. And here we had a whole cryogenics group. The cryogenics group, we needed 8 people to run the whole system. Today, you push a button, you get 7 millikelvin, you go home and so on. It's an amazing system. By the way, when we were doing this, the Axion experiment, we were doing manually everything. So Walter, is Walter here? No. Okay. Wunsch, he's at CERN working on Click. He was a classmate, a graduate student. He would move the microwave cavity rod, and then he say, what's the frequency on the spectrum analyzer? So I was saying, yeah, should I leave it there? Yeah, okay. So, after a while, I got tired of it. I said, Walter, I can make this automatic. I built the first auto system that was doing this. We were after that. It took me 2 weeks, and we could run the whole Axion experiment automatically day and night. Before that, it was only, when we were there, and we would stop for lunch and so on. And we also discovered the first candidate, Axion candidate. It's an amazing thing. I mean, it was a 10 sigma effect, but we turned off the magnet, it was still there. It was a radio station. We are still looking for them. That was the first attempt. Andrea Melisinos, when he did an experiment, he just ran extremely fast. In 3 years, we were done. I mean, extremely fast. All right. But to go higher in frequency is just very hard. This is from David Tanner, University of Florida. And it's just everything works against you, all right, with the old thinking. Orders of magnitude, so you cannot do it. ADMX went lower in frequency because it's easier. And John Clark, who got the Nobel Prize for this work, by the way, they developed the squids for them with a noise that was higher than 1K, but still. All right, that was their first attempt. This is Rochester, Brookhaven, Fermilab, University of Florida is here, and ADMX went lower. So going higher in frequency to get at the axion, theoretically interesting axion, it was hard, all right? And then there was a question whether we needed more resources to do that. It was felt that it is impossible to do that, all right? So what have we done since? Josephson parametric amplifiers, we developed that. Large volume magnets, large volume cavities cooled to 30 millikelvin and below. 22 millikelvin was our best. New resonating geometries and so on. High quality factors. CAPP, that's the Center for Action and Precision Physics Research in South Korea. We did all of that. We contributed to all of that. And we did get down to DFSZ sensitivities. And it was an amazing run. Absolutely. Impossible, you would think, but we succeeded in all of those. Okay? So these are the big opportunity right now is that we have a big magnet in Grenoble, and DALI provides the framework to reach the high frequency. So that's the effort we want to convince that's worth taking. This is the gray hull. That's the Grenoble magnet. It's an amazing 500 liter. This is the worm diameter. and this is the RF cavity diameter and so on. We would start actually from 200 megahertz, and we'll go all the way to whatever. Right now, we have already tested HTS cavity with 500,000 quality factor at more than 500,000 at 41 Tesla, and this thing survived. All right, we haven't published it yet, but this is under publication. I hope I'm not getting into trouble for saying this, but it's an amazing amount of data. So this is what we want to put together. We want to develop caramel so that we can have experiments at Grenoble. All right, so we have that and so on. Okay. So if we have done this, we have made so much effort and progress and so on, why are we not done yet? All right. So I'll tell you the reason for that. The reason I think so. We have a lot of activities. We can no longer claim that we don't have funding to do this, because there is a lot of action experiments around the globe. All right. So the idea. So what is the problem? All right. I have to tell you that if at LHC the people work the way we work in Action, we would still not know the Higgs mass. And that's the reason. All right. There are 10 million separate steps. All right. That's if you do the optimum, that is achieve 10 to the 6 quality factor. That's the optimum. All right. And so it would take more than 30 years of running time. So there are two major issues with action research and one possible solution. All right. The breakthrough advances are not being openly shared within the community. So everybody wants to get the Nobel Prize. This is a big problem. Suddenly, the Nobel Prize became from a motivation into a problem. It's sad. It truly is. All right. And at CABP, we had a policy. We always shared our technology. Achieving quantum level sensitivity continues to elude every experiment. It's not there yet. All right. With Carmen, we aim to reach better than DFSZ, and a parallel coordinated effort could achieve in less than a decade. So I'll tell you now very quickly that we develop special magnets, 1 to 8 gigahertz CABP can do, and 37 liters, so we reached down to 25 millikelvin, state-of-the-art JPAs. We have the best JPAs in the world. All right, so that's not an issue. We have everything for 1 to 8 gigahertz to do. Just to understand how Korea works, these are all members of our, most of them, not all of them, are members of CABP. This is at KAIST 2017. Look at the dates, January 2017. And this is experimental flow, isolation platforms. And this is 2011. In 4 years, we had 5, these are 4 over here, but we have more experiments, running experiments, all right? And we published and so on. So you see how Korea works. It's really, they gave us the money and they pushed us, and we took an amazing sprint to make everything happen, and it worked. I was surprised. I was afraid we will have a major accident, but that was my biggest fear. But everything worked fine. All right. The JPAs, why these are good? Squids have thermalization resistors, and those are noisy. These guys don't have resistors. They work just fine, but it takes a lot of know-how a lot of effort to make them work, and dedicated people like Çağlar Kutlu, a Turkish student from Turkey, he was from Smyrna, I think. And then Sergey, under the guidance of Sergey Yusakin, an amazing duo. All right, they made it happen, the very first one. And then the shielding of that is amazing. I mean, look at this. You turn on and off 8 Tesla magnet, and you have just a fraction of the quantum noise flux, quantum level flux. It's amazing. All right. And then, because those are very narrow, Sergey et al. Bundled them together so we can have very near the quantum noise. But you see, it's not quite the quantum noise. All right. So, and this is what we've done. In this reference paper, we describe everything. We tell you how the thermalization is done. It's not easy to thermalize things below 50 millikelvin, below 100 millikelvin. It's a different story. So you need to know that. And we explain how we achieve that. And now people are just running in Korea. They are still above the noise. 3 to 5 times means your running time is 10 to 25 times worse. So you need to bring them down to the quantum noise level. All right. The other thing is superconducting cavities. We were told not to do it, but we had no chance really, because without it. So we had to do it. The KAI's people are amazing. Condensed matter, surface physics, they understood that we can do it, and it's worth taking the chance. So we did it with KAIST, and we succeeded. All right. It took a lot of time. I told them, look, your failures are mine. Your successes are yours. And in the beginning, they don't believe it, but then they believed it. All right. And it worked finally. And we have, this is a 34-liter cavity, more than 1 million quality factor, and it's just unbelievable. All right. Why is this important? Because you can reach down the axion being 20% of the dark matter and still be able to reach DFSZ sensitivity with a reasonable scanning rate per year, right? 1 to 2, 2 to 4, 4 to 8. It's every octave. It's just amazing thing. The high frequency one. So Sang-Woo, he is now the director of the continuing center. He was the first one who succeeded in our impossible task to get efficiency in high frequency. And we were able to do it. You have to optimize it and then to do it. But it's a hard business. I mean, when you do it, first you fail, and then you fail, and then you fail, and then it works. All right. And when it works, people say, oh, I mean, in the meantime, they tell you it will never work. It will never work. And then it works. All right. So, by the way, he studied the alpha collaborations system, that the figure of merit for the alpha collaboration would be this. And he's concluded it's not good enough. And he got this figure of merit. So he ran an experiment with that, as a matter of fact. What alpha collaboration did is, these are metal posts, and then you can set the high frequency by geometry. But because you have a lot of metal, the quality factor goes down very quickly. So that's the problem. Sang-Woo solved this problem by using dielectrics. And this is what he was doing. He was using a kirigami to make it, to tune it. Now we want to use HTS-covered metals to get the high frequency, the high quality factor. And this is what we plan to do. The Alpha collaboration wants to do their own system. The idea of the IBS is an amazing one, all right? And Professor Jenny Kim was instrumental in putting our center together. And it was an amazing run. I was there for more than 11 years. Single photon detectors will make all the difference, all right? But caramel is not competing with that. So once the single photon detector works, we do it. But before that, we can use caramel, all right? And we can do a lot. I'm finishing, so. Okay, summary. So we have, those are mature experiments scheduled to complete the full frequency range a few decades. And DALI can help us with high frequencies, and hopefully we can get it done, even at Grenoble. So the key message is let's work together and get it done. Okay, thank you so much.
Okay, so now we have time for questions.
Thank you, Yannis, for the very nice talk. I have two questions. So the first one, what is the expectation, if you collaborate as a community to scan the whole interesting parameter range? You mentioned decade, 1 decade will be...
A decade is the target. If we don't collaborate, it's going to take 2 at least.
Okay. How is the collaboration thing going?
It's going very well.
Okay.
Very well. People, it's about trust and setting the correct rules. We have experience with that. And we can do it. If LHC did it, we can do it.
Indeed, yes. And the second question is about the status of CAP in terms of the future, because I know that the center has been very successful in doing this multi-prong approach to the direct detection. But it was there like 2 years ago, and it was not sure. I mean, this IBS way of doing things. No, they create and shut down institutes, and back in the day, it was not clear that it was going to be continuous.
Right.
So what was this?
But now we have the result. It's named DMAC, Dark Matter Action Group, headed by my former team leader, Sang-Woo Yoon. As I said, he was the first one to succeed with high efficiency, high frequency design. He's very good, no question about it. And it's the same program, the same place. I made sure KAIST keeps them there. So the president of the university promised me, no problem. And so it's continuing. It's important to keep the momentum, and this is happening. Korea pulled it off. This is difficult. I mean, if you think about most of our problems, you think about as social, right? And somehow Korea managed to keep it together.
Okay, is there any other question?
Oh, okay, thank you. I have a question about that kirigami structure for the cavity, because I mean, well, I'm not in this field, but just as far as I understand, you're really requiring very high precision in controlling all your instruments or small things.
Right.
So for this, can you really? It seems that you're putting force in one places, and you can really control, I mean, the precision of all structures, or.
Right. What happens is they have a dielectric structure inside the cavity, and they control it with a mechanism that sits outside the cavity, on the outside, with a single rotationary system, right? The postdoc, my former student at KAIST, he had dinner with his family, and his father is an engineer. And he was saying how difficult it is to move all of those. And his father said, "Why don't you use kirigami?" So it's good to have dinner with your family. Right. At the beginning, because room temperature, this thing works, no problem. But you cool it down, it doesn't, it gets stuck. So they had to have maybe 5 times attempts to make it work. And finally, they know how to make it work. Now it works. This postdoc now is a professor at Stockholm University, working for the competition, which is, the alpha collaboration. And this is what he's doing on the metallic structure. And it's a beautiful system he developed there. It works very well. Thank you.
Okay, any other question? Check if we have something here. Okay, there are no more questions, so please let's thank Yannis again. Now there will be coffee at the cafeteria, and students that want this counted, please come here before leaving.
Thank you so much.